So today we are going to be covering quite a lot of material, so I will try not to run, but then yesterday Jan scooped me completely, so Jan talked about exactly the same things I wanted to talk today, so I'm going to go a little bit faster. Please slow me down if you actually are somehow lost, okay? So I will just try to be a little bit faster than usual. So today we are going to be talking about recurrent neural networks. Recurrent neural networks are one type of architecture we can use in order to deal with sequences of data. What are sequences? What type of signal is a sequence? There is a temporal component, but we already seen data with temporal component. What are they called? What is the dimension of that kind of signal? So on the convolutional net lesson, we have seen that a signal can be a 1D signal, 2D signal, 3D signal based on the domain. And the domain is what you map from to go to, right? So temporal handling sequences of data is basically dealing with 1D data because the domain is going to be just the temporal axis. Nevertheless, you can also use RNN to deal with, two-dimensional data. You have double direction, okay? Okay, so this is a classical neural network in the diagram that I'm used to draw, where I represent each, in this case, bunch of neurons. Like each of those is a vector, and for example, the X is my input vector. It's in pink as usual. Then I have my hidden layer in green in the center. And then I have my final blue layer, which is the output network. So this is a 3-layer neural network for my notation. And so if some of you are familiar with digital electronics, this is like talking about a combinatorial logic. Your current output depends only on the current input, and that's it. There is no other input. Instead, when we are talking about RNN, we are going to be talking about something that looks like this. In this case, our output here on the right-hand side depends on the current input and on the state of the system. And again, if you're a keen of digital electronics, this is simply sequential logic, whereas you have an internal state. Jan yesterday mentioned flip-flop. If you have no idea what a flip-flop, check it out. It's just some very basic memory unit in digital electronics. Nevertheless, this is the only difference, right? In the first case, you have an output which is just function of the input. In the second case, you have an output which is function of the input and the state of the system, okay? That's the big difference. Yeah?
Why feed-forward is called vanilla?
Vanilla is an American term for saying it's plain, doesn't have a taste. That's American, sorry. I try to be the most American I can. Yeah, in Italy, if you take an ice cream which doesn't have a taste, it's going to be fior di latte, which is milk taste. In here, they don't have milk taste, they have vanilla taste, which is the plain ice cream. Okay, Americans, sorry. All right, so let's see, what does it change this with Jan representation? So Jan draws those kind of little funky things here, which represent a mapping between a tensor to another tensor, from one vector to another vector, right? So there you have your input vector, X, is going to be mapped through this item here to this hidden representation, so that actually represent my affine transformation, so my rotation plus the squashing. Then you have the hidden representation, then you have another rotation and squashing, then you get the final output, right? Similarly, in the recurrent diagram, you can have these additional things. This is a affine transformation squashing. That's like a delay module with affine transformation and squashing. And then you have the final one, affine transformation and squashing, right? This thing is making noise. Okay, sorry. All right, so what is the first case? First case is this one. It's a vector to sequence. So we input one bubble, the pink one there, and then you're going to have this evolution of the internal state of the system, the green one. And then as the state of the system evolves, you're going to be spitting out at every timestamp one specific output. What can be an example of this kind of architecture? So this one could be the following. My input is going to be one of these images, and then the output is going to be a sequence of characters representing the English description of whatever this input is. So for example, in the central one, we have a herd of elephants So the last one, a herd of elephants walking across a dry grass field. So it's very, very well refined, right? Then you have in the center here, for example, 2 dogs play in the grass. Maybe there are 3, but okay. They are playing in the grass, right? So it's cool. In this case, a red motorcycle parked on the side of the road where it looks more pink, or a little girl in the pink that is blowing bubbles that she's not blowing, right? Anything there. All right, and then you also have, even more wrong examples, right? So you have like a yellow school bus parked in the parking lot. Well, it's yellow, but it's not a school bus. So it can be failing as well, but it also can do a very nice, it can also perform very well. So this was from one input vector, which is for example, representation of my image, to a sequence of symbols, which are for example, characters or words that are making here my English sentence, okay? Clear so far? Yeah, okay. Another kind of usage you can have is going to be the following. So you're going to have sequence to final vector, okay? So I don't care about the intermediate sequences. So, okay, the top right is called autoregressive network. An autoregressive network is a network which is outputting an output given that you feed as input the previous output, okay? So this is called autoregressive. You have this kind of loopy part on the network. On the left-hand side, instead, I'm going to be providing several sequences. Yeah?
For the back to sequence, is like each blue, does maybe like the order matter at all? Like, is the first one always going to correspond to like the most important thing of the image? Or
that's going to be the English translation. So you have a sequence of words that are going to make up your final sentence. Each blue there, you can think about a index in a dictionary, and then each blue is going to tell you which word you're going to pick on an indexed dictionary, right? So this is a school bus, right? So a yellow school bus. You go to A, index of A, then you have second index. You're going to figure out that is yellow, and then school bus, right? So the sequence here is going to be representing the sequence of words the model is outputting. On the other side there on the left, you're going to have instead, I keep feeding a sequence of symbols, and only at the end I'm going to look what is my final output. What can be an application of this one? So something Jan also mentioned was this one. So let's see if I can get my network to compile Python, or to to interpret Python. So in this case, I have my current input, which I feed to my network, which is going to be j equal 8584, then for x in range 8, sum to j 920, blah, 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 and then print this one. And then my network is going to be tasked with giving me 25,011. Okay, so this is the final output of a program, and I enforce the network to be able to output me the correct output, the correct solution of this program. Or even more complicated things. For example, I can provide a sequence of other symbols which are going to be 8,827. Then I have C is going to be something. Then I have print this one if something that is always true as the other one. And then, the output should be 12,184, right? So you can train a neural net to do these operations. So you feed a sequence of symbols, and then at the output you just enforce that the final target should be a specific value, okay? And this thing is making noise. Okay, maybe better. All right, so what's next? Next is going to be, for example, sequence to vector to sequence. This used to be the standard way of performing language translation. So you start with a sequence of symbols, here shown in pink. So you have a sequence of inputs, then everything gets condensed into this kind of final H, which is this H over here, which is going to be somehow my concept, right? So I have a sentence, I squeeze this sentence temporal information into just one vector, which is representing the meaning, the message I'd like to send across, and then I get this meaning in whatever representation unrolled back in a different language, right? So I can encode, I don't know, today I'm very happy in English as a sequence of words, and then, you can get oggi sono molto felice, and then I speak also Italian today. Or whatever, today I'm very tired. 今天我很累. or whatever. Okay, so again, you have some kind of encoding, then you have a compressed representation, and then you get like the decoding given the same compressed version, okay? And so, for example, I guess, language translation. Again, recently we have seen transformers and a lot of things like in the recent time, so we're going to cover that the next lesson, I think. But this used to be the state of the art until 2 years ago. And here you can see that if you actually check, if you do a PCA over the latent space, you have that words are grouped by semantics, okay? So if we zoom in that region there, we're going to see that in the same location, you find all the months, December, February, November, and whatever, right? If you focus on a different region, you get that a few days, the next few months, and so on, right? So different location will have some specific, common meaning. So we basically see in this case how by training these networks, just with symbols, they will pick up on some specific semantic, features, right? In this case, you can see like there is a vector. So the vector that is connecting woman to man is going to be the same vector that is, woman minus man, which is this one, I think, is going to be equal to queen minus king, right? And so, yeah, it's correct. And so you're going to have that the same distance in this embedding space will be applied to things that are female and male, for example. Or in the other case, you have walking and walked, swimming and swam. So you always have this, specific linear transformation you can apply in order to go from one type of word to the other one. Or this one, you have the connection between cities and the capitals. All right, so one more, right? I think. What's missing from the big picture here? It's a big picture because it's so large, no? No, it's also a big picture because it's the overview. Okay, you didn't get the joke. It's okay. What's missing here?
Vector to sequence.
Vector to sequence. No, okay, good, but no, because you can still use the other one. So you have this one, the vector sequence to sequence, right? So this one, as you start feeding inside inputs, you start outputting something, right? What can be an example of this stuff? So if you had a Nokia phone and you use the T9, the stuff from 20 years ago, you have basically suggestions on what you're typing as you're typing, right? So this would be one type of these suggestions, where like one type of this architecture, as you're getting suggestions as you're typing things through. Or you may have like speech to captions, right? I talk and then you have the things happening below. Or something very cool, which is the following. So I start writing here. The rings of Saturn glitter while the harsh eyes, two men look at each other. Okay. They were enemies, but the servo robots weren't. Okay, hold on. So this network was trained on some sci-fi novels, and therefore you can just type something, then you let the network start outputting some suggestions for you. So, if you don't know how to write a book, then you can, ask your computer to help you out. Okay, that's so cool. Or one more that I really like it. This one is fantastic, I think. You should read it. I think, so you put some kind of input there, like the scientist named, hold on, what is it? Oh, the prompt, right? So you put in the top a prompt, and then you get, this network start writing about very interesting unicorns with multiple horns. Horns. It's a unicorn, right? Okay. All right, that's so cool. Just check it out later. You can take a screenshot of the screen. Anyhow, so that was like the eye candy, such that you get, hungry. Now let's go into BPTT, which is the thing that Jan really liked yesterday. BPTT, he said. Okay. All right, let's see how this stuff works. Okay. So on the left-hand side, we see again this vector, middle, hidden representation, the output, the to-affine transformation, and then there we have the classical equations, right? All right, so let's see how this stuff is similar or not similar. And you can't see anything, so for the next 2 seconds, 1 minute, I will turn off the lights, then I turn them on. Okay, now you can see something. All right, so let's see what are the equations of this new architecture. Don't stand up, you're going to be crushing yourself. All right, so you have here the hidden representation now. It's going to be this nonlinear function of this rotation of a stack version of my input to which I appended the previous configuration of the hidden layer, okay? And so this is a very nice compact notation. It's just, I just put the two vectors one on top of each other. And then I sum the bias. I also define an initial condition. My initial h is going to be 0. So at the beginning, whenever I have t equal 1, this stuff is going to be set as a vector of zeros. And then I have this matrix WH is going to be two separate matrices. So sometimes you see this equation as WHX times X plus WHH times H t minus 1. But you can also figure out that if you stack those two matrices, you know, one attached to the other, then you just put these two in vertical, right? It's completely equivalent notation. But they look like very similar to whatever we had here. So hidden layer is a fine transformation of the input. Hidden layer is a fine transformation of the input and the previous value, okay? And then you have the final output is going to be, again, my final rotation. So I'm going to turn on the light. So no magic so far, right? You're okay, right? You're with me. Two shake the heads. What about the others? No. Yes. Okay. Whatever. So this one is simply, on the right-hand side, I simply unroll over time, such that you can see how things are just not very crazy. Like this loop here is not actually a loop. This is like a connection to the next time steps, right? So that round arrow means it's just this right arrow. And so this is a neural net. It's simply a neural net which is extended in length, rather also not only in thickness, right? So you have a network that is going this direction, input and output, but also you can think as this being an extended input and this being an extended output, while all these intermediate weights are all shared, right? So all of these weights are the same weights. And then you use this kind of shared weights. So it's similar to a convolutional net in the sense that you had this parameter sharing, right? Across different time domains, because you assume there is some kind of, stationarity, right, of the signal. Make sense? So this is a kind of convolution, right? You can see how this is kind of a convolution, right? All right, so that was kind of, a little bit of the theory. We already seen that. So let's see how this works for a practical example. So in this case, we are just reading this code here. So this is word language model. You can find it at the PyTorch examples. So you have a sequence of symbols. I just represented there every symbol as like a letter in the alphabet. And then the first part is going to be basically splitting this one in this way, right? So you preserve vertically the time domain. But then I split the long sequence such that I can now chop. I can use batch computation. So the first thing, you have the batch size is going to be 4 in this case. And then I'm going to be getting my first batch. And then I will force the network to be able to, so this is going to be my batch back propagation through time period. And I will force the network to output the next sequence of characters, okay? So given that I have ABC, I will force my network to say D. Given that I have GHI, I will force the network to come up with J. Given MNO, I will force the network to get P, and STU, force the network to get V, right? So how can you actually make sure you understand what I'm saying? Whenever you are able to predict my next word, you're actually able to, you're basically knowing already what I'm saying, right? Yeah. So by trying to predict the upcoming word, you're going to be showing some kind of comprehension of whatever is going to be this temporal information in the data. All right, so after we get the batch, we have, so how does it work? Let's actually see in a bit of a detail. This is going to be my first output. It's going to be a batch with 4 items. I feed this inside the recurrent neural net, and then my neural net will come up with a prediction of the upcoming sample, right? And I will force that one to be my BH and T, okay? Then I'm going to be having my second input. I will provide the previous hidden state to the current RNN. I will feed this inside, and then I expect to get the second line of the output, the target, right? And then so on, right? I get the next state, the next input, I get the next state, and then I'm going to get inside the neural net, the RNN, which I will try to force to get the final target, okay? So far? Yeah?
Can you say explicitly what is H1 here?
H1 is going to be the output of the hidden net, recurrent neural net, right? I showed you the equation before. You have H1 comes out from this one, right?
But in that sequence, which letter will be output?
Say again?
In that specific case, what will be, can you say explicitly what will be the output?
The output, I'm going to be forcing the output actually to be my target, my next word in the sequence of letters, right? So I have a sequence of words, and I force my network to predict what's the next word given the previous word.
So H1 will be equal to X2?
No, H1 is going to be fed inside here. And you stack the next word together with the previous state. And then you do a rotation of the previous word with the new word with the next state. The new word with the previous state. You do a rotation here, fine transformation, right? And then you apply the nonlinearity. So you always get a new word that is the current X, and then you get the previous state just to see in what state the system was, and then you output a new output, right? And so we are in this situation here. We have a bunch of inputs. I have my first input, and then I get the first output. I have this internal memory that is sent forward, and then this network will now be aware of what happened here. And then I input the next input, and so on. I get the next output, and I force the output to be the output here, the value inside the batch. Okay. All right, what's missing now?
Are you taking 3 items at a time because for memory constraints?
This is for PowerPoint drawing constraint. All right, what's happening now? So here I'm going to be sending here I just draw an arrow with the final HT, but there is a slash on the arrow. Why there is a slash on the arrow? Who can understand what the slash means?
Because there is nothing beyond that time sequence.
Oh, of course there will be. There is going to be the next batch. It's going to be starting from here, D, and so on. This is going to be my next batch, DJPV, EKQV, and FLRX.
Backpropagating through a very long sequence is going to take a lot.
Right, so this slash here means do not backpropagate through. Okay, so that one is going to be calling dot detach in torch, which is going to be stopping the gradient to be propagated back to forever. Okay, so this one say no batch, and so whenever I get the no gradient, such that when I input the next gradient, the first input here, it's going to be this guy over here, and also of course without gradient, such that we don't have an infinite length RNN. Okay, make sense? Yes, no. I assume it's a yes. Okay, so vanishing and exploding gradients. We touched upon this also yesterday. So again, I'm kind of going a little bit faster today than usual. So let's see how this works. So usually, for a recurrent neural network, you have an input, you have a hidden layer, and then you have an output. Then this value of here, how do you get this information through here? What does this arrow represent? Do you remember the equation of the hidden layer? So the new hidden layer is going to be the previous hidden layer which we rotate, right? All right, so we rotate the previous hidden layer. And so how do you rotate hidden layers? Matrices, right? And so every time you see a horizontal arrow, there is a rotation, there is a matrix. Now if this matrix can change the sizing of your final output, right? So if you think about perhaps, let's say the determinant, right? If the determinant is unitary, it's going to be mapping the same areas to the same area. If it's larger than 1, then you're going to be getting, these gradients to getting larger and larger. Or if it's smaller, then you're going to get these gradients to go to 0 whenever you perform the backpropagation in this direction, okay? So the problem here is that whenever we send gradients back, so the gradients are going to be going down like that, are going to be going like down like this, then down like this way, and down like this way, and also all down this way, and so on, right? So the gradients are going to be always going against the direction of the arrow. And each arrow has a matrix inside, right? And again, this matrix will affect how these gradients propagate. And that's why you can see here, although we have a very bright input, that one gets lost through. Or where if you have like a gradient coming down here, the gradient gets, killed over time, okay? So how do we fix that? To fix this one, we simply remove the matrices in this horizontal operation. Does it make sense? No? Yes?
No.
No. The problem is that the next hidden state will have, its own input memory coming from the previous step through a matrix multiplication. Now this matrix multiplication will affect what's going to be the gradient that comes in the other direction. Okay? So whenever you have an output here, you have a final loss, and then you have the gradient that are going to be going against the arrows up to the input. The problem is that this gradient, which is going through in the opposite direction of these arrows, will be multiplied by the matrix, right? The transpose of the matrix. And again, these matrices will affect what is the overall norm of this gradient, right? And it will be or killing it, you have vanishing gradients, or you're going to have exploding gradients, which is going to be, whenever it's going to be getting amplified, right? So in order to be avoiding that, we have to avoid, so you can see this is a very deep network. So a recurrent neural network were the first deep networks back in the 90s, actually, and the depth was actually in time. And of course, they were facing the same issues we face with deep learning in modern days. Wherever we were stacking several layers, we were observing that the gradients get lost as depth, right? So how do we solve gradient getting lost through the depth in current days?
By using skip connections.
Skipping connection, right? The residual connections we use. And similarly here, we can use skip connections as well when we go down, up in time, okay? So let's see how this works.
I have a question.
Yeah.
Do you do the forward and the backward propagation, both of them, with removal?
So the problem is that the gradients are only going in the backward path, right?
In back propagation, you remove the matrices.
Well, the gradient has to go the same way you went forward by the opposite direction, right? I mean, you're computing chain rule. So if you have a function of a function of a function, then you just use those functions to go back, right? The point is that whenever you have these gradients coming back, they will not have to go through matrices. Therefore, also the forward part doesn't have to go through the matrices, meaning that the memory cannot go through matrix multiplication if you don't want to have this effect when you perform back propagation, okay? So,
but isn't this going to change the actual performance at the end?
yeah, it's going to be much better working. I'll show you in the next slide.
Sure, in terms of the
No.
gradient issue, is not going to have vanishing gradient or exploding gradient. So what about the prediction?
Yeah, show you next slide. So how do we fix this problem? Well, instead of using one recurrent neural network, we're going to using 4 recurrent neural networks, okay? So the first recurrent network, the first network is going to be the one that goes from the input to this intermediate state. Then I have other 3 networks, and each of those are represented by these 3 symbols, 1, 2, and 3, okay? Think about this as an open mouth, and this is like a closed mouth, okay? Like the emoji, okay? So if you use this kind of 4 recurrent neural network, big recurrent network, you're going to have, for example, from the input, I send things through the open mouth, therefore it gets here. I have a closed mouth here, so nothing goes forward. Then I'm going to have this open mouth here, such that the history goes forward. So the history gets sent forward without going through a neural network matrix multiplication. It just gets through an open mouth. And all the other inputs find a closed mouth, so the hidden state will not change upon new inputs, okay? And then here you're going to have a open mouth here, such that you can get the final output here. Then the open mouth keeps going here, such that you have another output there. And then finally you get the last closed mouth at the last one. Okay. Now, if you perform backprop, you're going to have the gradients flowing through the open mouth, and you don't get any kind of matrix multiplication. So now let's figure out how these open mouths are how are they instantiated in terms of mathematics. Is it clear, this one, right? So now we are using open and closed mouths, and each of those mouths plus the first guy here that connects the input to the hidden are going to be RNNs. So this one here, that is a gated recurrent network. It's simply 4 normal recurrent neural network combined in a clever way, such that you have multiplicative interaction and not matrix interaction. Okay? Is it clear so far? This is like intuition. I haven't shown you how. All right, so let's figure out who made this and how it works, okay? So we're going to see now those long, short-term memory or gated recurrent neural network. So, sorry. Okay, that was the dude. Okay, this is the guy who actually invented this stuff. Actually, him and his students back in 1997. And we were drinking here together. Okay, all right, so that is the equation of a recurrent neural network. And on the top left, you're going to see the diagram. So I just make a very compact version of this recurrent neural network. Here is going to be the collection of equations that are expressed in a long short-term memory. They look a little bit dense, so I just draw it for you here, okay? Let's actually go through how this stuff works. So I'm going to be drawing an interactive animation here. So you have your input gate here, which is going to be an affine transformation. So all of these are recurrent network, right? The same equation I show you here. So this input transformation will be multiplying my C tilde, which is my candidate gate. Here I have a don't forget gate, which is multiplying my previous value of my cell memory. And then my total cell is going to be don't forget previous plus input second. I'm going to show you now how it works. Then I have my final hidden representation. It's going to be multiplication, element-wise multiplication between my output gate and my, whatever hyperbolic tangent version of the cell, such that things are bounded. And then I have finally my C tilde, which is my candidate gate. It's simply a recurrent network, right? So you have one recurrent network, one that modulates the output, one that modulates, this is don't forget gate, and this is the input gate. So all this interaction between the memory and the gates is a multiplicative interaction. And this forget input and don't forget input and output are all sigmoids. Therefore, they are going from 0 to 1. So I can multiply by a 0, you have a closed mouth, or you can multiply by 1 if it's an open mouth, right? If you think about being having an internal linear value, which is below -5 or above +5, okay? Such that you use the gates in the saturated area, or 0 or 1, right? You know, the sigmoid. So let's see how this stuff works. This is the output. Let's turn off the output. How do I turn off the output? I simply put a 0 inside. So let's say I have a purple internal representation C. I put a 0 there in the output gate. The output is going to be multiplying a 0 with something. You get 0. Okay? Then let's say I have a green one. I have a 1. Then I multiply 1 with the purple. I get purple. And then finally I get the same value. Similarly, I can control the memory, and I can, for example, reset it. In this case, I have my internal memory, C, this is purple, and then I have here my previous guy, which is going to be blue, I guess. I have a 0 here, and therefore the multiplication gives me a 0 there. I have here a 0, so multiplication is going to be giving a 0, I sum two zeros, and I get a 0 inside the memory. So I just erase the memory. And you get the 0 there. Otherwise, I can keep the memory. I still 0 the internal thing, the new one, but I keep a 1 there, such that the multiplication gets blue, the sum gets blue, and then I keep sending out my blue. Finally, I can write such that I can get a 1 in the input gate. The multiplication gets purple. Then I set a 0 in the don't forget, such that he actually forgets. And then multiplication gives me 0. I sum the two, I get purple, and then I get the final purple output. Okay. So here we control how to send, how to write in memory, how to reset the memory, and how to output something. Okay. So we have all different operations. This looks like a computer almost. And in the
by the saturated sigmoid,
Yep.
does this mean that we treat the sigmoid operation like a binary?
I assume in this case to show you like how the logic works, as we are like having a value inside the sigmoid as being or below -5 or being above +5, such that we are working as a switch, 0-1 switch. Okay.
Is that just for the purpose of this demonstration, or is that like how it would actually work?
The network can choose to use this kind of operation. To me, makes sense. I believe this is the rationale behind how this network has been put together. The network can decide to do anything it wants. Usually, they do whatever they want, but this seems like they can work. At least if they saturate the gates, it looks like things can work pretty well. So in the remaining 15 minutes, or kind of, I'm going to be showing you two notebooks. I kind of went a little bit faster because, again, there is much more to be seen here in the notebooks. So
I still had a doubt.
Yeah?
So when we compute gradient of C with respect to W,
Yep.
still we'll have repeated multiplications with the weight matrix, right?
So the actual weight, the actual gradient you care here is going to be the gradient with respect to previous C's, right? The thing you care is going to be basically the partial derivative of the current C with respect to previous C's. Such that if you have the original initial C here, and you have multiple C over time, and you want to change something in the original C, you still have the gradient coming down all the way until the first C, which comes down to getting gradients through that matrix WC here, right? So if you want to change those weights here, you just go through the chain of multiplications that are not involving any matrix multiplication, and such that when you get the gradient, it still gets multiplied by 1 all the time, and it gets down to whatever we want to do. Okay. Did I answer your question?
But I still did not understand how is repeated multiplication by weights matrix being avoided.
So the matrices will change the amplitude of your gradients, right? So if you have like the largest eigenvalue being 0.0001, every time you multiply, you get the norm of this vector getting killed, right? So you have like an exponential decay. In this case, if my forget gate is actually always equal to 1, then you get C equal C minus T. Derivative, what is the partial derivative of CT with respect to, what is the partial derivative of CT with respect to T minus 1?
It will be
1, right? So the partial derivative, that is the thing that you actually multiply every time, is going to be 1. So output gradient is going to be input gradient, right? Yeah. Output gradient is going to be input gradient because you multiply the output gradient by the derivative of this module, right? If the derivative of this module is 1, then the thing that is here keeps going. That is the rationale behind this.
Does this require the sigmoids to be saturated all the time?
No, this is just for drawing purposes. I assume it's like a switch, okay? Such that I can make things, you have a switch on and off to show like how it should be working. Maybe it doesn't work like that, but still it works. It can work this way, right? Yeah?
I have a question. What if the input sequence, they're not of the same sizes? Like you have different sizes of sentences, right? How would you make that into a batch of one size? So
that's the implementation question. It's going to be simply, you just pad all the other sequences with zeros before the sequence. So if you have several sequences, several sequences that are of different length, you just put them all aligned to the right, and then you put some zeros here. Okay? Such that you always have in the last column the latest element. If you put zeros here, it's going to be a mess in writing the code. If you put zeros in the beginning, you just stop doing back propagation when you hit the last symbol, right? So you start from here, you go back here, so you go forward, then you go back prop and stop whenever you actually reach the end of your sequence. If you pad on the other side, you get a bunch of crap there. In the next 10 minutes, we are going to be seeing two notebooks. if you don't have other questions. Okay. Wow, you're so quiet. Okay, so we're going to be going now for sequence classification. All right, so in this case, I'm going to be, I'll just read this stuff out loud. The goal is to classify a sequence of elements. Elements and targets are represented locally, input vectors, with only one non-zero bit, so it's a one hot encoding. The sequence starts with a B for beginning and ends with a E for end. And otherwise consists of a randomly chosen symbols from a set A, B, C, and D, which are some kind of noise. Expect for two elements in position T1 and T2. This position can be either or X or Y, okay? For the hard difficulty level, you have, for example, that the sequence length is chosen randomly between 100 and 110. T1 is randomly chosen between 10 and 20. T2 is randomly chosen between 50 and 60. There are four sequences, classes, Q, R, S, and U, which depends on the temporal order of X and Y. So if you have XX, you're going to be getting a Q. X and Y, you get an R. Y and X, you get an S, and YY, you get U. So we are going to be doing a sequence classification based on the X and Y or whatever those two these kind of triggers, okay? And in the middle, you're going to have A, B, C, D in random positions, or like, randomly generated. Is it clear so far? So we do classification of sequences where you may have these X and Ys, or XX, or YY, or YX. So in this case, I'm showing you first the first input. So the return type is a tuple of sequence of 2, which is going to be what is the output of this example generator. And so let's see what is this thing here. So this is my data I'm going to be feeding to the network. So I have 1, 2, 3, 4, 5, 6, 7, 8. There are 8 different symbols here in a row every time. Why there are 8? We have X and Y, A, B, C, and D, beginning and end, right? So we have one hot out of 8 characters, and then I have a sequence of rows, which are my sequence of symbols. Okay. In this case, you can see here I have a beginning with all zeros. Why is all zeros? Padding, right? So in this case, the sequence was shorter than the maximum sequence in the batch, and then the first sequence has an extra 0 item at the beginning. And then you're gonna have like, in this case, the second item is of the tuple is the corresponding batch class. For example, I have a batch size of 32, and then I'm gonna have an output size of 4. Why it's 4? QR whatever, right? The QRSU. Okay, so I have a 4-dimensional target vector, and I have a sequence of 8-dimensional vectors as input. Okay, so let's see how this sequence looks like. In this case, it's going to be the beginning, BX, CX, CBE. So XX, let's see, XX. XX is Q, right? So we have a Q sequence. And that's why the final target is a Q, the 1000. And then you're going to see B, BX, C. So the second item and the second last is going to be B, lowercase b. You can see here the second item and the second last item is going to be a B. Okay? All right. So let's now create a recurrent network in a very quick way. So here I can simply say my recurrent network is going to be torch NN RNN. And I'm going to be using a ReLU network, ReLU nonlinearity, and then I have my final linear layer. In the other case, I'm going to be using LSTM, and then I'm going to have a final linear layer. So I just execute these guys. I have my training loop, and I'm going to be training for 10 epochs. So in the training loop, you're going to be always looking for those 5 different steps. First step is going to be get the data inside the model, right? So that's step number 1. What is step number 2? There are 5 steps, you remember? Hello? You feed the network with some data. Then what do you do? you compute the loss. Okay. Then we have compute. Step 2, compute the loss. Fantastic. Number 3, you zero the cache, right? Then number 4, which is computing the
Of loss with respect to weight.
Loss dot backward.
yes, loss dot backward. What does loss dot backward do? Compute the partial derivative of the loss with respect to the network's parameters. Yeah. Here, backward, finally, number 5, which is
Updating the parameter.
step in opposite direction of the gradient. Okay? All right. Those are the 5 steps you always want to see in any training loop, right? If someone is missing, then you're fucked up. Okay. So we train now the RNN and the LSTM, and you get something looks like this. So RNN got up to 50% in accuracy, and then the LSTM got 100%. Okay. Oh. Okay. First of all, how many weights does this LSTM have compared to that RNN? 4 times more weights, right? So it's not a fair comparison, I would say. Because LSTM is simply 4 RNNs combined somehow, right? So also it's a 2-layer neural network, whereas the other one is a 1-layer, right? Or whatever. Like it has 1 hidden layer, the RNN, the LSTM, we can think about as having 2 hidden. So again, 1 layer, 2 layers, well, 1 hidden, 2 hidden, 1 set of parameters, 4 sets of the same numbers. Okay, not fair. Okay, anyway, let's go with 100 iterations, okay? So now I just go with 100 iterations and I show you how, if they work or not. Then also I'm gonna be just clicking things such that we have time to go through stuff. Okay, now my computer is going to be complaining. All right, so again, what are the 5 types of operations? 5. Okay, no, it's already done. Sorry, I was going to do. Okay, so this is the RNN, right? RNN, and finally, it actually gets to 100%. Okay. So RNN, you just let it more time, like a little bit more longer, train, and it actually works. The other one, okay, and here you can see that we got 100%. In 20 epochs, okay? The other case, we got 100% in roughly twice longer the time, okay? So let's first see how they perform here. So I have this sequence, B, C, Y, D, Y, D, A, E, which is a U sequence, and then we ask the network, and the actual network actually labels it as U. Okay, so below, we're gonna be seeing something very cute. So in this case, we were using sequences that are very, 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 very small, right? So even the RNN is able to train on these small sequences. So what is the point of using LSTM? Well, we can first of all increase the difficulty of the training part, and we're going to see that the RNN is going to be miserably failing, whereas the LSTM keeps working. In this visualization part below, okay, I train a network, an LSTM now, with the moderate level, which has 80 symbols rather than 8 or 10 symbols. So you can see here how this model actually managed to succeed at the end, although there is like a very big spike. And I'm going to be now drawing the value of the cell state over time, okay? So I'm going to be inputting now a sequence of 80 symbols, and I'm going to be showing you what is the value of the hidden state. So in this case, I'm going to be showing you I'm going to send my input through a hyperbolic tangent such that if you're below minus 2.5, I'm going to be mapping to -1. If you're above 2.5, you get mapped to +1, more or less. And so let's see how this stuff looks. So in this case here, you can see that this specific hidden layer picked on the X here, and then it became red until you got the other X, right? So this is visualizing the internal state of the LSTM. So you can see that a specific unit, because in this case I use hidden representation, like hidden dimension of 10. And so in this case, the 1, 2, 3, 4, 5, the fifth hidden unit of the cell, like the fifth cell, actually is triggered by observing the first X, and then it goes quiet after seeing the other X. And this allows me to basically, take care of, recognize if the sequences are U, P, R, S. Okay, does it make sense? Okay. There is one more notebook I'm going to be showing just quickly, which is the eco data. In this case, I'm going to be set kernel. I'm going to have a network echoing whatever I'm saying. So if I say something, I ask the network to say if I say something. I ask the network to say if I say something. Okay, you understand, right? Okay. So in this case here, I'm going to be inputting, this is the first sequence. It's going to be 0, 1, 1, 1, 1, 0. And then you have the same one here, 0, 1, 1, 1, 1, 0. And then you have 1, 0, 1, 1, 0, 1, etc., right? So in this case, if you want to output something after some time, right? This case is 3 time step after. You have to have some kind of short-term memory where you keep in mind what I just said. Where you keep in mind what I just said. Where you keep in mind what I just said. Yeah, that's correct. So, parroting actually requires having some kind of working memory. Whereas the other one, the language model, which it was prompted to say something that I haven't already said, right? So that was a different kind of task. You actually had to predict what is the most likely next word. You cannot be always right? But this one, you can always be right. There is no random stuff. Anyhow, so I have my first batch here, and then the Y batch, which is the similar thing, which is shifted over time. And then we have to chunk these long sequence. So before, I was sending the whole sequence inside the network, and I was enforcing the final target to be something, right? In this case, I had to chunk, if the sequence goes this direction, I had to chunk my long sequence in little chunks. And then you have to feed the first chunk, keep trace of whatever is the hidden state, send a new chunk where you feed as initial hidden state the output of this chunk, right? So you feed this chunk, you have a final hidden state, then you feed this chunk, and as you had to put these two as input to the internal memory, right? Then you feed the next chunk, where you put this one as input to the internal state. And we are going to be comparing here RNN with an LSTM, I think. So at the end here, you can see that, we managed to actually get with RNN a accuracy that goes 100%. Then if you are starting now to mess with the size of the memory chunk, with the memory interval, you're going to be seeing that with the LSTM, you can keep this memory for a long time, as long as you have enough capacity. The RNN, after you reach some kind of length, you start forgetting what happened in the past. And that was pretty much everything for today. So stay warm, wash your hands, and I'll see you next week. Bye-bye.